Okay, so today my talk is matrix models with so what I will basically describe today is some of my previous work with Prashant Samantre and Azuma, and some of my ongoing work with Anosh and Kasi. So I'll say show you some simulation, etc., which is going on, and let's see. So the first thing is that let me start with the phase diagram of QCD and how does it look like. So in the axis of temperature and chemical potential, if you look at the phase diagram of QCD, and what do I mean by QCD is basically an SU3 theory with NF is equal to 3. Now, to be honest, this kind of phase diagrams are very complicated, depends on the details of the masses involved, masses of the fundamental particles, etc. But roughly speaking, and I will be little imprecise here, don't want to go to the details of QCD phases, which is not my primary interest. Is basically it looks like this. And so this is a deconfined phase. This is confined phase. And in the middle, have like this is confined phase. So in this kind of phase diagram, there are, roughly speaking, there are two chemical potential. As you increase the chemical potential, first you hit the nuclear matter phase where there is a non-zero baryon density, and then you go to the deconfined phase. Roughly this is the phase diagram. So you have two phase transition, here you have a critical point, here you have a critical point, deconfined, confined phase, and nuclear matter, etc. As I'm saying that this phase diagram is a little bit imprecise. It depends if you change the mass, this changes, but this is the rough phase diagram. Now, if you look, other than the QCD, say if you look at say some pure SU-N gauge theory, say SU4 gauge theory or something like that, well, then there is, of course, no chemical potential because we have taken out the matters, etc. But it seems that the temperature axis, at least, is a confinement This is a confinement deconfinement phase transition. Interestingly, what happens is that as you introduce matter, it is generally believed that this phase transition goes ahead. And there is a rough, large way of understanding it. So what happens is that generally, in a large gauge theory, so free energy in the confined phase is of the order 1, and in the deconfined phase of the order n square, where n is the number of degrees of freedom. Now, if you have enough number of fundamental flavor, this is for pure, but once you have flavors, this is roughly equal to order nf square. And this free energy remains order n square plus something. So as you increase the number of nf, the difference between two phases, again, it depends on the details of the theory, but roughly you can say that the difference between the phases actually decreases, and at some point you may expect that having number of flavors will get rid of this confinement deconfined phase transition. And this is indeed the case in some lattice simulation, etc. And in some lower dimensional 0+1 dimensional model, we have also shown similar things in our previous work, that indeed if you introduce flavor, this transition goes there. Now, today I'd like to explore this chemical potential axis a little more.
You have to introduce a critical number of flavors?
Yeah.
So suppose NC was 100.
So if there is some ratio of NC by NF in the large N limit.
These guys are carrying both the color index and the flavor index.
Yes, so this N square calculation is not exactly precise.
So but then it will be enhanced also by the flavor factor. So how does
That actually is a good point. That actually is a good point. So this counting argument is not exact, but because of the various large N limitations, one can show that even in the deconfined phase, it is not just a sum of N square plus NF square, actually a bit less than that. Okay, and for that reason, no, not times. Why time? Gluons.
Independent of square plus NF. NF. Right. Suppose NF is smaller than NP, N square is long.
So in any case, this NF comparison to NM is what?
Then only it will happen. Yeah, so you have to put a lot of fundamental paper.
Order N, alpha type.
Advanced form is
No,
Advent codes, I think it's the fun.
fundamental. So all matters are fundamental. All fundamental matters. Okay. Now, so the question is that what happens if you introduce chemical potential? So basically, if you introduce chemical potential, okay, so one motivation of our work means what we are going to do is that, as I'm saying that this kind of rough description of this model can be achieved in lower dimensional theory. At the end, we can study few lower dimensional theory to get his phase diagram, which is not very different than this kind of phase diagram. So if you have a theory, in lower dimension, they strongly coupled, etc., it is much easier to do numerics. So basically, at the end of the day, one...
Just to understand what is believed. So suppose N is large enough, it means that when NF by N is less than a certain order 1 number,
Yes.
there is a phase transition, and when NF by N is
Exactly.
less than that, there is no phase transition.
Exactly. Yeah, but that's only on the temperature axis. In the chemical potential axis, the story is a little different. Okay, so basically we want to do numerics and find out the phase structure of a lower dimensional theory. Now, so comes.
What is the order of this number alpha that she has?
Nobody knows. It depends on the details of the theory. Order 1.
Order 1, you still want
So, for example, in this kind of theory, if you look at it, is like 0.3 or 0.4.
but it's well below, it's still asymptotically.
Yeah,
I think it started that.
yeah. So, okay, this computer has died for some reason. Is it true?
crossover point from the lattice for other
Well, N is equal to 4 and 5 people have studied, I think.
crossover point.
Crossover point depends on many things. And even in lower time, I think that SU2 gauge theory, there is even a debate that whether there is at all a phase transition. So even in pure SU2. So depends a little bit on the details of the theory.
Isn't there a separate phase transition with the guidance you mentioned?
Yeah, possibly, of course, massless things. But
Massive.
yeah, but I'm not getting into that today, so I did not. Okay, so let me get into the main question of our talk is that what happens if you have chemical potential? So basically, let us just discuss very simple model. So if you have boson models or something like that, say, a charged boson dt, and so just one-dimensional charge boson, phi1 and phi2 are two components, so it's a complex field basically. If you want to solve this theory on a lattice or something, what you do basically, you do an analytic continuation like that, tau is equal to et, it or something you put, and then the action conveniently becomes something like and say this is put from 0 to beta on the tau is an imaginary time, and one can simulate this action, which is a positive definite, on any computer very easily, not super easy all the time, but in principle you can do a simulation with this kind of action. Now what happens, what is the interesting thing is that what happens if you have also a chemical potential in the theory. Suppose if you introduce chemical potential for so this is like mu I2 okay. Basically, you have a single derivative term in time. If you have any kind of current, you put a chemical potential for it, a single derivative term in current. And once you do this complexification trick, this will still survive as a complex quantity to something. So basically action becomes complex. There is a d0 square, this it goes away, but here it will still remain complex. Yes. Sorry? I into mu. This is the mu phi square, mu square phi square kind of term. The charge has two terms. One is del zero and is like phi square. So the point is that but this del zero term is problematic. This goes with the mass, but this gives a complex number once you analytically continue. So if you have complex numbers like that, you cannot generally solve these equations, at least numerically. Why it is that, let me discuss a little that how do you solve this equation numerically? So there are many ways. So if you have a very simple action like this, so the simplest of the quantum field theories, say, zero-dimensional. And then the question is that how would you solve this equation on computer? So this equation is pretty easy to solve in computer. One way to do is through Monte Carlo method. Why this equation is easy to solve is that how this looks is something like this. This function, right, with x. And if a function has a very well-defined peak, what Monte Carlo method, etc., can do is the sample near this peak and consequently give a good numerical approximation of the probability distribution. However, a very simple generalization of this equation is super difficult to solve in a computer. For example, from this action, if we come to a simple action like this, this action, so the real part of which basically e to the power minus ax square into cos bx. So if you draw the real of this z or something like that, real of this quantity, then you get a curve like this. So if this is something like this, so what happens is that this value of this integral crucially depends on the cancellation between positive and negative parts. And just sampling where it is maximum would give you a very wrong answer. Right. So one interesting question is that how to solve this integral, even this simple integral, numerically. Monte Carlo does not do it. So one crude way of solving this integral is to do a phase quench approximation. Basically, you calculate, you generate your probability distributions through this formula, and then density function depends on that. And then in this density function, you basically calculate this quantity. So that will give you number one method of solving this integral. This gives us a very bad answer. Generally, if beta b is a little large, then this is not the best way to do things. Then, yes, say, not eventually, I would not, but.
So you're saying you're generating the ensemble by e minus a.
Right.
And in that, you want that.
Yeah, this is called phase quenched approximation often. Sorry?
When you compute the observables,
Yeah.
you are putting in this way.
Yes, exactly. But this is not a very good approximation because this doesn't sample the probability distribution easily. Yes. Okay. Only works if b is small. Okay, so what is the second method of doing it? One can do various stuff, but if I give you this integral, how you do it analytically? So analytically, this integral is done quite easily by completing the into some e to the power some quantity. So if you complete the square, then this integral can be easily done. Now, when you complete the square, basically you are diagrammatically, what you are doing is that you had, suppose we look at this integral in the complex plane, although it is a real integral, you are basically shifting the line of the integral to some other point, and interestingly, on that contour, this integral is actually a positive definite integral. It does not have any fluctuation. Once you do the shifting, you go to a new contour. On this new contour, this integral is no more a fluctuating integral, but just like a simple Gaussian integral. So, this simple analytic solution gives us some idea about how these integrals could be solved, is that we basically move out in the complex plane, and in the complex plane, there could be some contour on which these integrals are positive definite. If we find out such contours, then these integrals could be solved.
way of.
That is true. That is true. So it may not work in various cases in practice, but at least this idea, we can put it in practice and see that if it works or not. Okay. Now, this kind of shifting of contours, etc., cannot be done by Monte Carlo, at least not obviously. But there are other methods of quantization which we can generalize to complex variables more easily. So one method of quantizing a simple theory is the second method of quantization, called stochastic quantization. What is the idea of stochastic quantization? Stochastic quantization is that, suppose if we write down this equation, sorry.
Respect to B, then also you would get something which would, which you might, so that would also.
Yeah, but Fourier transform we don't want to do, means at the end we are not going to solve a Gaussian integral, we'll solve a nonlinear integral, and if you do Fourier transformation, the theory become nonlinear. If you have, means that it become non-local also, so there are problems, etc. Okay. We'll come to that. But you are saying that Fourier transformation on one field, right? Yeah, so that may work, but that also does not work because, again, if you have to solve the Fourier transform theory, what happens in most cases, the saddle point value of the chemical potential itself will become complex. And getting the real chemical potential may be a little, there are issues, we will come to that. Let's just move into stochastic quantization procedure. The stochastic quantization is that, suppose if I give you this equation, okay, so this is a random, it's a normal 0-1 number. So this is a stochastic differential equation, and for this stochastic differential equation, there is a corresponding Fokker-Planck equation which says how the probabilities evolve with time. Okay. And this Fokker-Planck equation is pretty easy to solve, and you will find that this probability, the saddle point means that static value of this probability distribution will be given by P, T at infinity, will be given by e to the power minus sx. This is a stochastic time. Okay, so okay, yes. Call it some stochastic time, some other variable, not real time, right, good point. So at large, this stochastic time or whatever, you expect that this steady state probability distribution of this theory will be something like e to the power minus sx, will sample this value. So this is the idea of stochastic quantization. Now, sorry? Yeah. Eta, the coefficient in front of eta will come here. But if this coefficient is 1, nothing is there. So, because I have taken a normal 0-1 for this thing. So you exactly get e to the power minus sx. But even this stochastic quantization would not work because this equation would not be a real equation if we do a stochastic quantization. It will become a complex equation because this action itself is complex. Yes, the thing is that idea is that you have this stochastic differential equation, you simulate stochastic differential equation in computer, and you expect that the large value of this stochastic time tau, you actually reach.
So you get this, but then what is that accomplished for us is what I missed.
You get this. So that is the accomplishment. You try to get e to the power minus sx by some. You want to sample some distribution. That's the.
Okay, so this is for some given distribution, but in our case, because it's complex, it's not going to work.
Yeah, it's not going to work directly because the stochastic equations itself will become complex. If you look at this dynamics like dz rather than minus s dash j dt plus some eta r plus I eta I dt rho dt, this dynamics will take us away from the real line. And then this so basically what happens is that this dynamics won't be confined in the real line and may take us away. Now people have claimed, and there are some proof there also, but very hand-waving proof, which I am not going to show now, is that there is a claim and proof that if you do that, if you do this to simulate this stochastic dynamics, eta r is equal to 1, it's like before, and it's just real, there is no complex component there, but this part has a complex component, then what you get is a two-dimensional Fokker-Planck equation, and correspondingly is two-dimensional probability distribution in the complex plane. Right. If it converges at all, if this dynamics converges at all. And people have claimed and has proved to some extent is that if you look at observable with a two-dimensional interval of this kind for some observable, and if this is an analytic function, this is same this is over the whole z plane, and this is over the real line. This rho xt is not positive definite. And in large time, it is believed that this equation should hold, large stochastic time. Rho x infinity is what we like to simulate, something like this, which may not be a real quantity. Yeah. Rho x infinity, OX, this x means, again, this is stochastic time, at large stochastic time, you simulate it for a long time. So this rho x infinity, or what, this is actually rho x infinity, or I must say that this is e to the power minus sx of OX is same as this quantity. The difference is that e to the power minus sx is not a positive definite quantity. But claim is that this pxy is a two-dimensional probability distribution in a complex plane. This is a positive definite quantity. So this thing can be guessed or calculated through the stochastic dynamics and could be well, possibly could be well approximated by O should be holomorphic. Otherwise it doesn't work. That's the claim at least. And sometimes it does work, but there is, yeah. So, but the basic claim is that O has to be holomorphic for this procedure to work. So this claim was made by many people over the time, starting from Ambron and those people who recently got Arts, who is in Swansea. So a lot of the lattice people are using those kind of procedures. So I'll take 2-3 more minutes, or 5 more minutes. Okay?
That's an area integral.
That's an area integral.
And that is
That's a line integral.
use some Stokes theorem?
Something similar. When it is proved that they use something similar to Stokes theorem. Basically, you know, these line integrals basically can be deformed in complex planes, right? This is this function and normalized to 1, etc. So these contours can be deformed, right? Because if you have integral over the real line, you can deform it over to the complex plane, means some other contour. And what we are doing in essence is that we have put some weight on that contours. So I'm saying that this integral on the real line is okay, same as this integral over a contour, but let us also put a weight over various contours and do the integral. Roughly this has been done. And this, because getting the exact contour where the phase is constant is difficult for a large dimensional problem. But this Pxy can be simulated easily through stochastic dynamics. So why is this not working? Sorry?
Just to clarify, rho is
Exactly.
and P is something that you calculate.
Yeah, P is, we'll something to calculate from this dynamic.
Is there a systematic way to compute P? Or?
Exactly. P is systematically computed numerically through simulating these dynamics or this dynamics in the complex plane.
Right. What I'm saying is, you know the thing that you know, right?
Yes, no, yes, because rho means we know S. So S dash Z we know. And from that, we can complexify the fields and do the dynamics in the whole complex plane and get the results. Yeah, so.
Is there a case that P is now O is also not a positive definite function for sure.
O may not be. O may not be.
What you really want to compute is rho of x O.
And look, if O is not a positive definite function, it's generally very difficult to do those computations.
O Z is certainly not because for the model. So how do we make it positive?
O is never a positive definite function because you just simulate a probability distribution, and from that probability distribution, if it is, for example, say O is like, say,
Actually,
OX could be a very simple function like Z square, say. Okay, so that means that suppose if you look at the real part of O, it is just x square minus y square. So you basically do an x square pxy computation minus y square pxy computation. You have some cancellation between two positive numbers here, but just two cancellation. Whereas in the previous integral, if B is large, you have huge number of huge series of valleys and peaks.
is there a claim that P is positive? Is there
P is positive.
P is positive.
P is positive because P is a probability distribution.
I see. But
P is the resulting probability distribution of that stochastic process I have written down there.
this two and I mean two cancellations versus many cancellations is a little troubling because
It is a huge difference. You will see. You'll see a huge difference. And these cancellations are not also cancellation in a sense that, look, if you have a large N theory, etc., both are order 1 numbers and they differ quite a bit, x square and y square. The one is 1, one is 0.3. It's not even a close cancellation. So we can get a good approximation of the theory. But if you IBX, so if you take B is equal to 10 or 20, and if some large factor n or something is sitting in front of the integral, then there are huge numbers of values and peaks. Very difficult to do those calculations. It's much easier to do this calculation. So basically what I have done here is that, you see that in the complex plane, sorry? No, sorry? No, I did not. Oh, okay. So we are coming to this kind of thing, okay? So this is minus x square or something like that. So it is just e to the power minus x square. So we will, stochastic dynamics will sample it over the real line as it should. Now, if we move away from that point, so something like this. So now this is u square minus 3iu. Yeah, so I'll show you. Here, what is, so this is the stochastic differential equation which I've written down. If you get rid of the stochastic part, this is a vector flow equation in 2 dimensions. X dot is equal to something, y dot is equal to something. So this where you see these resulting vector fields. And then what I'm doing is that I'm plotting the trajectory of a stochastic point which has been marked red here. There are millions of points. So we start from some point and see that how it is evolved. And the question is that whether it has really sampled a point near the point it should, means that what is that zeros of this v dash z. Of course, one could be careful and calculate those quantities and match with the analytic results, and they do find that it actually matches. Now, this is a simple demonstration of the stochastic calculation, and we can get more complicated. Now, as I'm not much time, I'll show that what I'm doing now is that suppose, let me just get into the main thing. We are doing this same stochastic differential, this same kind of quantization for 0 plus 1 dimensional theory. But give 0 plus 1 dimensional theories. Now, before going into 0 plus 1 dimensional theory, today I'll show you simple results of something like if you have just a 0 dimensional theory. This is Painter's favorite model, I think. But now this model comes with a twist that A and B are not same. This is a matrix model, which I think Painter solved, etc. Don't have time to go into the details. Generally, it is solved like A trace U plus trace U diagram. But if you take a model where A and B are different, A not equal to B, and you get a very similar model if you have chemical potential for fundamental matters, etc. So what happens is that, again, from our discussion, what we have learned is if is it to B, then this model has eigenvalues distributed in the Z plane over a circle, because this is an unitary matrix model. All the points are distributed over a circle like this. Circle of radius 1. Once A not equal to B, this is a complex model, and if you solve it through a saddle point equation, you will find we can solve it analytically, but we have this gapped and ungapped, various things, but the first interesting thing is that saddle point solution of this equation are no more on Z r is equal to 1, they go out in the complex plane. When A not equal to B, the saddle point equations are no more on the unit circle, they go out in the complex plane. So the first exercise, what I tried to do is that I tried to solve this model using complex Langevin method. And this blue curve is somehow the point we should get. This is the circle on which the eigenvalues are lying. One can analytically solve it, not going into the method, a little bit involved. And then this is the circle, R is equal to 1 circle, where it was before if the model were complex. And these red points are the results of my Langevin dynamics equation. How the Langevin dynamics equal. So we see that at least for these simple models, this Langevin dynamics can approximate, can get the right contour in the complex plane. Now one may ask that one knows various things like ρ1, the expectation value of trace U square, etc., and try to match from this simulation and the exact results. that approximately matches, but this Langevin dynamic is also not very exact now for various technical reasons. But this, even with a simple thing, we can get, and basically we can get this thing. And now this does not converge very well, and one has to do various things like change of variable and adaptive time, step size, etc. But still, at least you can get this kind of eigenvalue distribution through Langevin dynamics. Now our goal is to go in other theories, 0+1 dimensional theories, etc., and see that if we can reproduce some part of the QCD phase diagram. So this is the end of my talk. Suppose you have simple Z2 model, which you want, or SU2 model, which you want to solve. Generally, if these two things are same, this SU2 model becomes e to the a cos theta plus log of sine theta, and one can, analytical means one can get the saddle points very easily. But when A not equal to B, even in SU2 model, if you solve this model, what you will find is that the saddle point values of theta is not a real number. It is theta real plus I theta imaginary. That's why the Z, if you plot, if it is e to the power I theta, is e to the power I theta real into minus e to the power I theta I. So this is no more, the saddle points are no more lying in the unit circle, they go out of it. So that gives me interesting dynamics, etc. Oh, that's very small value of A and B. A was like 0.2. N. Oh, N was possibly around 50 or 100 or something like that.
Why is there so much spread? It didn't look like it was coming apart.
No, N is equal to 50 is, okay, so, okay.
As n goes, it should go to a line.
No, yes and no. No, at N is equal to infinity, it does not go into, what happens, I'll tell you. Yes, but what happens is that if you look at this stochastic differential equation, suppose depending on the step size dt, there is a width. So if you plot these things, plot one snapshot or few snapshot of the eigenvalues, they do not quench on a line. What will happen is that
Time average.
yeah, time average quench. Time average of the trace u squared, those things will be. But those are more scientific to plot, but I have just shown you a visual demonstration of this thing.